According to the standard model of particle physics, muons are fundamental particles, particles not made of lesser components. The problem with this assertion is, once formed, a muon decays into an electron and a couple of neutrinos in a fraction of a second. In the oxymoronic spirit of quarks, particles that allegedly exist, but one can never see, the standard model considers muons, particles that disintegrate into three fundamental particles, to also be fundamental. How can something that is fundamental decompose into three other fundamental things? It can't. Contrary to what the standard model claims, muons are apparently made of component particles. Continue watching to see why muons are not fundamental. Part 1 of this series showed that, around 1970, the Stanford Linear Accelerator Center, SLAC, along with particle physicists from the Massachusetts Institute of Technology, MIT, interpreted electron-proton deep inelastic scattering experiments they did in ways to corroborate the three-quark proton model proposed by Murray Gell-Mann. However, 30 years later, the Jefferson Lab, JLab, produced scattering data that, when combined with the SLAC data, showed the proton is actually made of 9 particles, not 3. This is because the combined SLAC-JLab proton F2 structure function values, when plotted as a function of x, the proton momentum fraction, peak at x equals 1/9. The x, where the F2 peaks, is the reciprocal of the number of particles forming the proton. The SLAC-JLab F2 peak at 1/9 indicates the proton is made of 9 particles. Based on the mass those particles should carry, 1/9 the proton mass of 1,836 free electron masses, or about 204 free electron masses, they appear to be muons, which have a free mass of 207 electron masses, not quarks. Unfortunately, to date, this analysis has yet to be formally acknowledged. Between the time of the SLAC and the JLab experiments, electron-proton deep inelastic scattering was also done at HERA, the Hadron Electron Ring Accelerator. In deep inelastic scattering, the wavelength of the probing electron is roughly 1 over the square root of the momentum transfer, q squared, of the collision. Because HERA ran at much higher q squares than SLAC and JLab, up to 1,600 GeV squared versus less than 1 GeV squared near the SLAC-JLab F2 peak, the wavelengths of its probing electrons were as much as 50 times shorter than those of SLAC and JLab. This allows them to see much finer detail within the proton than the SLAC and JLab electrons. The SLAC and JLab electrons do not see anything smaller than the muon inside the proton. However, the HERA F2 values rise above the SLAC and JLab F2 values between x equals 0 and x equals 1/9, indicating that its electrons are seeing things smaller than muons within the proton. The F2 data from one of the first sets of HERA runs covers 16 momentum transfers, q squared, for 14 momentum fractions x, ranging from x equals 0.133 down to just under x equals 0.0002. For each x, F2 values were measured for at least 2 q squareds. For x values that have F2 values for more than 3 q squareds, a phenomenon called scaling sometimes becomes evident. Briefly, as q squared increases for a given x, the F2 initially rises, then levels off for a stretch of q squareds before continuing to rise. The stretch of relatively constant F2s is where the scaling occurs. It indicates that the probing electrons have focused on objects within the target. The average of the F2 values for the range of Q squared values measured for a given X typically falls within the scatter of the range of the scaling values for that X. These averages will be the F2 values used for a given X value in the following analyses. When plotted with the SLAC and JLab data, the HERA average F2 values appear to form an F2 curve, sitting on top of the SLAC JLab F2 curve, starting at X equals 1/9. This is the F2 curve of the proton components, presumably the muons. The proton momentum fraction, X equals 1/9, is the momentum fraction of a whole muon on the proton F2 graph. Therefore, it corresponds to a momentum fraction of X equals 1 on a muon F2 graph, the momentum fraction of a whole muon. The SLAC JLab peak proton F2 value of about F2 equals 0.36, occurring at X equals 1/9, is the maximum F2 contributed by the muons in the proton. Anything above 0.36 is the additional contribution of the components of the muon to the total F2 measured by HERA. Therefore, subtracting the SLAC JLab peak proton F2 value from the HERA F2 values gives the F2 values for the muon component particles. In other words, the proton structure function F2 equals 0.36 is the muon structure function F2 equals 0. By making the noted adjustments, a muon F2 curve can be plotted using the average F2 values from the HERA deep inelastic scattering data. The muon F2 data has a sharp peak near X equals 0. A plot of the data for momentum fractions between X equals 0 and X equals 0.1 shows that the peak occurs at roughly X equals 0.005. Analyzing the data points using curve fitting reveals that the muon F2 curve likely peaks at X equals 0.0049. Since the reciprocal of 0.0049 is 204.1, the muons in the proton appear to be made of just over 204 particles on average. Recalling that the mass of the muons in the proton is 204 free electron masses, the muon appears to be made of particles with masses essentially equal to the mass of the electron. With the negative muon having a unit negative charge, and the positive muon a unit positive charge, to achieve these, it seems reasonable to conclude that the muon component particles carry either a unit negative or unit positive charge. If that is the case, then the muon component particles appear to be some form of electrons and positrons. The muon is made of electrons and positrons. The muon F2 curve peak, occurring at X equals 0.0049, corresponds to a peak on the proton F2 curve occurring at X equals 0.0049 divided by 9, or X equals 0.000544. The reciprocal of this X, 1,836.7, or 1,837 in whole numbers, is the number of the muon component particles making up the proton. Since the proton has a unit positive charge, it must be made of 5 positive muons and 4 negative muons, one more positive than negative. If the particles forming the muons are electrons and positrons, then a negative muon must contain one more electron than positron, and a positive muon, one more positron than electron. One way to accomplish this for a proton made of 1,837 electrons and positrons is for the positive muon to contain 205 particles, 102 electrons, and 103 positrons, and the negative muon, 203 particles, 102 electrons, and 101 positrons. 5 times 205 plus 4 times 203 equals 1,837. Since the proton has an exact mass of 1,836.153 free electron masses, the component particles of the muon appear to have an actual mass of 1,836.153 free electron masses divided by 1,837 particles, or 0.99954 times the mass of a free electron. The particles that form the muon, and ultimately the proton, look like electrons and positrons, but are slightly less massive than free electrons and free positrons. Beta decay of nuclei may explain this small difference. When an isotope undergoes negative beta decay, it emits an electron and an electron antineutrino. For example, hydrogen-3 emits an electron and an electron antineutrino to become helium-3. Similarly, if an isotope decays via positive beta decay, it emits a positron and an electron neutrino. Nitrogen-13 emits a positron and an electron neutrino to become carbon-13. The neutrinos appearing during the decay appear to hold the key to the mass difference of electrons and positrons inside versus outside of a proton. During beta decay, in addition to the particles emitted, some of the mass of the decaying nucleus is converted to energy and dissipated, many times as a gamma. If the nucleons within the nucleus are made of electrons and positrons, then the source of that energy is likely electron-positron annihilation. The mass of a free neutron is 1,838.688 free electron masses, about 2 1/2 free electron masses more than a free proton. So neutrons are likely protons containing 3 extra particles, 2 electrons and 1 positron, less some binding energy. A nucleus needs the right combination of protons and neutrons to be stable. If it has too many or too few neutrons, one way it can adjust the number is via beta decay. If one of the extra electrons within the nucleus interacts with a positron, it can initiate a limited chain reaction of annihilations. Those annihilations produce a burst of energy and reduce the mass of the nucleus. The energy apparently creates an electron-neutrino-antineutrino pair and kicks either the antineutrino and a surplus electron, negative beta decay, or the neutrino and a surplus positron, positive beta decay, out of the nucleus. Note that during negative beta decay, the antineutrino appears, but the neutrino does not. And during positive beta decay, the neutrino appears, but the antineutrino does not. It seems that the exiting electron in negative beta decay, call it a beta electron, couples with the neutrino created during the decay to form a free electron, leaving the now unpaired antineutrino to escape as a decay product. Likewise, the exiting positron in positive beta decay, call it a beta positron, couples with the antineutrino to form a free positron, and the unpaired neutrino becomes a decay product. Now, a beta electron from within the proton couples with an electron neutrino to form a free electron that, because of the neutrino, is slightly more massive than the beta electron. Similarly, a beta positron from within the proton couples with an electron antineutrino to form a free positron that, because of the antineutrino, is slightly more massive than the beta positron. Both the free electron and the free positron have much larger diameters than their beta counterparts. The reason for this is due to the free electron magnetic moment and will be discussed in the next video. So, the electrons and positrons that are the component particles of the muons inside the proton are standalone beta electrons and beta positrons, while the free electrons observed in nature are a beta electron coupled with an electron neutrino, and the free positrons are a beta positron coupled with an electron antineutrino. The Hera electron proton deep inelastic scattering showed that muons are not fundamental particles, as the standard model of particle physics claims, but are made of more than 200 beta electrons and beta positrons. Further analyses showed that free electrons observed in nature appear to be the beta electrons found inside the muons, coupled with electron neutrinos, and free positrons observed in nature appear to be the beta positrons found inside the muons, coupled with electron antineutrinos. Consequently, free electrons and free positrons, also claimed by the Standard Model to be fundamental, appear to be made of component particles too. The next video develops physical models of the electron and the muon based on descriptions proposed here and well-established physical constants that show them to be complex particle systems, not fundamental, and shows once again that particle physics has failed.